All right, great. Okay, so good morning, everyone. At the joyous beginning of the National Science Day celebrations conducted by us, the Science Club of IISER Pune, I wholeheartedly welcome you all to the first event of our Life of an Eminent Scientist series. Today at us, we have Dr. Bindu Bambah, Professor in the School of Physics at the University of Hyderabad. Professor, we gladly welcome you to this talk. So today, Dr. Bambah will be giving us a talk on the life and work of the renowned physicist, Professor Yoichiro Nambu, who won the Nobel Prize in Physics in 2008. This talk is extremely special because Dr. Bambah received her PhD under the guidance of Professor Nambu, whom she would be talking about today. She received her PhD in theoretical physics from the University of Chicago. Dr. Bambah's research interests are in group theory and Lie algebra, quantum squeezing and entanglement. She also works on the links between particle physics, cosmology, quantum optics, and mathematics. She was also a scientific associate at the Center for European Nuclear Research, CERN, Geneva. Dr. Bambah was awarded the UNESCO Rosca Young Scientist Award for South Asia in 1991 and many international publications and awards. In addition to her scientific contributions, Dr. Bambah has written articles and given seminars to women's study groups, both in India and abroad, to devise methods of adopting and training women to assume leadership roles in the physical sciences. Professor, we are happy to have you here with this session. I think we can begin with the talk now.
Okay, thank you. Share my screen.
Share your screen?
Yeah. Okay, so I'll just start the slideshow. Yeah, just a second. So it's really nice. Thank you for the introduction. And can you see my full screen now?
Yes, visible.
Okay, great. So thank you very much for the introduction. I have been once to your institute and it was very nice. It was a very nice experience and I have many friends that are on your faculty. So I'm very happy to give this talk, especially since it pays homage to my thesis supervisor. And I would like a lot of people to know about him. So this, this is a picture of Professor Nambu taken on December 10th, 2008, just after he received the Nobel Prize. So I'm going to talk. A lot of people may not have heard of him, but people in advanced particle physics courses may have heard of him. So he was a physicist ahead of his time. He's been called all these things, the foreteller of modern physics, the unassuming genius. And because he was so unassuming, maybe, not many people have heard of him. What happened is that in October, all of us, we look forward to the Nobel Prizes. And for Indians, the first thing we do is we check if an Indian got the Nobel Prize. And then, of course, all the newspapers and all the clubs, rejoice in the vicarious glory. The second thing we do is see if we have been personally affected by the Nobel Prize. Perhaps the next best thing to winning the Nobel Prize is if someone close to us wins the Nobel Prize. And or somebody who shared his knowledge with us. And so then we are the legatee of his noble thoughts. And so I struck the jackpot in 2008 when I was just sitting in my, watching the screen and the Nobel Prize was announced and it was for Professor Yoichiro Nambu for the discovery of the spontaneous broken symmetry in atomic physics, subatomic physics. And the other half was shared with Kobayashi and Masukawa for the discovery of the origin of broken symmetry, which predicts the existence of at least 3 families of quarks in nature. So the thing is that both of these Nobel Prizes were given to some aspect of symmetry. In fact, some aspect of symmetry violation. So broken symmetry or spontaneous broken symmetry and the The other violation is the CP violation, which is that is charge and parity violation, which Kobayashi and Maskawa got the award from. So these Nobel Prizes came very late in Professor Nambu's life. I mean, they came when he was 86 years old. One of the reasons could be that that this was after the Higgs boson was discovered. So it was recognized that the Higgs boson, really the prediction of the Higgs boson rests on Nambu's work. And therefore, probably the Nobel Committee finally woke up and gave him a Nobel Prize 40 years after his seminal work. So when Professor Nambu received the prize, we talked, and one of the things he says is that while a religious person seeks these answers in organized religion, a scientist seeks the answers in the material world by following the scientific method. And I will tell you about the method that Professor Nambu followed. In particular, particle physicists seek a unity of all the forces of nature, and a tool by which this unification takes place is symmetry, and the mathematics of this symmetry is group theory. And not only is symmetry important, but as we shall see, the breaking of symmetry is also important. We don't like the breaking of symmetry. We love symmetric objects. We always make objects in art symmetric, but sometimes even broken symmetry is very beautiful. And this is what both Professor Nambu and Kobayashi and Maskawa recognized. So the thing about unification is that it takes place at very high energies, and we were not able to achieve those high energies as yet at which unification would take place. We were able to reach at those energies at which two of the forces of nature, the electromagnetic and the weak force, are unified, but at the LHC. But we hope that in the future we may be able to reach much higher energies, and probably not up to the Big Bang, but that would be very optimistic. But we would try to find ways in which we could infer that unification took place. And the whole idea of unification rests on this idea of Nambu's of spontaneous symmetry breaking. And so, but that's not all he did. I mean, he has a very large body of work. And he's the founding father of string theory. He's the first person to conceive of string theory. And he has conceived of what is called color, a quantum number that holds quarks together in nuclei, and also which explains the stability of matter. And that is actually an exact symmetry. So he was a very mild, modest man, and he always dressed in black suits, always. And he always mystified us with his mind that made connections between very different fields of physics, very different ideas of physics. For example, the work that he got the Nobel Prize for connects superconductivity, which you study in your condensed matter course, with quarks in nuclei, which you study in your nuclear and particle physics course. So he was able to build bridges between different fields of physics. And I'll talk about some of this later. So, and we always knew that we must really listen to him, because and many people said this, including Edward Witten. He said that, what Nambu thinks of today will be the truth 10 years later. And even today, some of my students work on problems that were given, suggestions that Professor Nambu gave 25 or 30 years ago, and they're still important. So it was really fitting that 47 years after he opened up the universe, he got a Nobel Prize. And he was a real fan of India, and he had three Indian students. Professor Shumit Das, who's a string theorist at the University of Kentucky and at TIFR. He has a double position. Dr. Madhushree Mukherjee, who is a best-selling author, and she writes, she's a senior editor for Scientific American, and myself. And he always had a good friend, George Sudarshan, who he did talk who they talked about Indian philosophy a lot because George Sudarshan was very interested in Indian philosophy. And so this is, he, over the years, his Indian students and admirers gave him a set of Ganesha, mostly to do with the dancing Shiva, because that represents high energy physics. And so here he is with some of his Indian mementos on his desk. So I'm going to give you a brief history of his life. And the reason I'm going to give you a brief history is because it tells you the story about how a scientific principle is developed. So you can see how a combination of fate and personal character of the scientist brought him or her to the point of discovery. So in that way, the retelling of the history of famous scientists helps you in sort of seeing that they were also fallible, as fallible as you, and they were also had doubts, and they were also they had curiosity, they had doubts, and in order to satisfy their curiosity, they came up with these wonderful ideas, and so you can probably learn something for their lives, and that's why I'm going to give you this brief history of their life. So he was born in Tokyo on January 18th, 1921. And last year we had his centenary celebration. Unfortunately, it had to be online on Zoom. He developed an interest in science while in high school. And a lot of us do develop our interest in science in high school. And he had to leave Tokyo when he was 2 years old because of an earthquake, and he settled in Fukui, Japan. And there his father had a very good library. He grasped ideas which helped him to escape from the regimen of a very militaristic school. In those days in Fukui, the schools were very, very militaristic and regimented, and he did not enjoy going to school because it was so regimented. So he spent a lot of his time reading in his various books, including we'll see books on political philosophy, Marx, etc. And his originality came from having to think through himself at a very early age, because the school was very regimental. So if he wanted to understand something, he would like to think it through himself. So he was awarded the bachelor degree from Tokyo Imperial University. But remember then, a little later, the war broke out. So World War II broke out for Japan. And he was greatly influenced by Hideki Yukawa, who had proposed that in a nucleus, the force that binds the nucleus together is not just a field or a wave, but it is due to an exchange of a particle, which was called the pion. So he was really intrigued by the fact that particles are carriers of force, and that was that was a unique and new idea in that time. And Professor Nambu was in Tokyo University when Professor Yukawa conceived of this idea. And then in 1947, he married his wife. This is a photograph of Professor and Mrs. Nambu. After the war, during the war, actually, Professor Nambu was working in a radar lab. He was recruited, but not for active duty. He was there in a radar lab, and I'll talk a little bit about this. So after the war, he took up a position of lab assistant in Tokyo. And, this is very interesting because it was, Japan lost the war, right? So he said that of this period, he said that I was hungry all the time, and finding food and calculations in physics took up his time. So these were the only two activities that he, finding food for his family and doing physics. So in 1950 at Osaka University, Nambu published his first paper. And of course, it is about this idea of the force being carried, a force being generated through the exchange of particles. So it was called force potentials in quantum field theory. And it worked out Yukawa's conjecture that nuclear forces were transmitted by exchange of pi mesons. Ironically, the equations that appear in his paper are called, of course, Western equations, Bethe-Salpeter equations. I mean, this is always happening in physics, that the equations are always named after the Westerners, even though Professor Nambu and had already done these. But I guess there was no internet and there was no archive in those days. But it was an example of the fact that he always had this facility of clairvoyance, the faculty of perceiving things or events in the future. So he earned his doctorate in physics from University of Tokyo in 1952. And then what had happened is that during the war, he had been asked to look at some documents, some secret documents. And these documents happened to be authored by one of the inventors of quantum field theory called Tomonaga. And then and after he used that to write this paper, and it was read by Robert Oppenheimer at the Institute of Advanced Study. And so he was invited to the US. And he suffered feelings of inadequacy almost to the point of a nervous breakdown, because when he went to Princeton, he thought that everybody was smarter than him. Everybody, and he recalls staying on the same street as Einstein, and that every day he would go to the ice cream van, because Einstein loved ice cream. So just to get a glimpse of Einstein and to say hello to him, he would go to the ice cream van. So he recalls but he said that, he was really overwhelmed by his inadequacy, and that made him work even harder and try to prove himself even more. Ultimately, he got a research associate position in Chicago, where he stayed for almost the rest of his life, except for the last few years. And he quickly, but you see that he joined as a research assistant in 1954, and he became a full professor in 1958. So it was a meteoric rise, and it was good that the University of Chicago actually recognized his genius very well. And at the year I joined, he had just been named a distinguished service professor. And as I told you, he was very fond of India, and this is a picture of him in front of I think Halibid and Belur, the temples at Halibid and Belur, because he visited Bangalore in 1982. This is a picture of him then. So let us see what was his philosophy, because that is something you will learn from, since you are now starting out a life in science, or maybe. In 1957, he proposed a new particle which had strangeness quantum number at a conference. It was called a rho meson. And the funny thing is that this was met with ridicule even by Richard Feynman. He ridiculed the existence of such a particle. Professor Nambu felt a little bit bad that he had made this prediction of a rho meson, which was discovered a year later. But he was governed by a special type of philosophy, which he had come into contact with when he was a student at Tokyo University. At that time, remember, there were many, many great minds at Tokyo University, and a lot of them had been conscripted in the war. And they all influenced each other, and they had long sessions of discussion. And the two physicists come philosophers that really influenced Professor Nambu were Sakata and Takatani. And Sakata and Takatani, besides Sakata as being known for the first person to introduce something like the quark model, I mean, in the sense that he introduced a model to explain the uniformity of masses of proton, neutron, and a strange particle. He also talked about mixing of the neutrino mixing matrix also has Sakata's name in it. But besides doing physics, Sakata was very much interested in the method of science. How does one do physics? And so with his fellow postgraduate friend, Takatani, Sakata and Takatani, they developed a new philosophy of how science should be done. And this is called the Sakata-Takatani philosophy. And it greatly influenced Nambu's thinking. So, when you listen to the philosophy, it's somewhat like a Marxist philosophy of science. That is, Marxist philosophy says there are 3 stages of a revolution: thesis, antithesis, and synthesis, right? First you rebel, first you establish a system, then you rebel against it, and then you go to a new system, right? So this is what, it's called dialectic materialism. And the theory of Sakata and Takatani was this dialectic materialistic theory of science. And so the 3 stages of this theory was: first, you start from phenomenal stage, where you describe your experience. So that means first you observe. So you observe regularities, you observe mass, you observe phenomena through various experiments. Then you ask what sort of substance make up the objects of experience and what is the structure they may have. So first you observe the object, then you question what is it made out of, okay? So there are many ways to then investigate that. And and then from these 2 stages, you extract out things which are independent of the substance, okay? So you make a theory, some sort of universal theory out of it, and the process then is reiterated again and again and again. So this was the 3-stage theory of Sakata and Takatani, and it is very different from. So this was the Japanese school of thought. It's very different from a parallel school of thought that was being developed in England. Mainly practitioner of that school of thought was Professor Dirac, and his thing was that if you use logic, and the logic guides you in certain ways, and you formulate your logic in terms of mathematics, and you follow the mathematics, it will give you physics. And that is how Dirac predicted the positron, which was measured. So that was the Dirac school of thought. That is, you go from logic to experiment. And this school of thought was you go from experiment to theory. Okay. And, in India, we have examples of both types of this method being practiced. I mean, for example, Professor Sunil Mukhi at your institute practices the Dirac mode, in that he does string theory, and they look for the as far as the logic will take them for the unification of forces. Whereas because I'm trained by Professor Nambu, I follow this aspect, and therefore I involve myself with experiment also first. I have taken here quotation from Professor Nambu when he was describing the 3-states theory, and I'll read it out. So, they were both Yukawa student and worked on the meson theory with Yukawa. Sakata is the more famous and more talented a person. When Takatani was a student in the in the 1930s, he started out right away from theoretical views of his about how physics develops. That is now called Takatani's three stages theory, namely that physics goes through three stages repeatedly. First, the phenomenological stage, when you discover something new in nature and you really don't understand that, and you have to study and get the data and find some form of regularity, some kind of law there. When you try to explain that regularity in terms of some kind of hypothesis, in terms of some kind of particles or whatever, the first stage is called the phenomenon, or it is the phenomenological stage. For example, you had conservation of mass in the 19th century and regularities in chemical reactions, and initial sum of mass equals final sum of mass, which you explain in terms of some kinds of elementary particles or units of mass. So that's the kind of explanation that comes at the second stage. But that is not the final story. And one really has to find more detailed or precise mathematical framework. So the mathematics comes at the end in this. So Faraday's law had to work into Maxwell's theory, and Maxwell's theory had to go to Maxwell's equations. So according to Takatani, that is not the end of physics. So eventually they will come a new phenomenon, which you cannot explain in the existing theory. So we have to start all over again. So that was the philosophy under which Professor Nambu was trained. So he divided his thinking into two basic categories. He called it the reductionist approach and the generalist approach. So the reductionists first try to find a symmetry or regularity in phenomenon and trace it to the properties of the fundamental particles. For example, the eightfold way of classifying particles by Gell-Mann. He looked at regularities in their quantum numbers. And similarly, even Mendelev's periodic table, it looked at regularities in the chemical properties and then placed them into categories. So that is an example also of reductionism, and you could explain them by their atomic structure. So that was the reductionist part of the periodic table. And similarly, Gell-Mann could use the mathematical tool of quarks to figure out the structure of the masses of the hadrons that were discovered much later. So there are two types of, and then he also said that what you have to do is you have to then extract from the particular, you have to extract out the general. Okay, so you have to see what applies to everything, not just the particular phenomenon that you are studying. And this is a very universalist view of science. It is not dependent on your prejudices. Okay, and also he was very concerned with symmetry. So two types of symmetries are there: space-time and internal symmetries. And space-time symmetries and gauge theory of electromagnetism was established in the early half of the 20th century. And then internal symmetries came in the latter half. So, but we find that these internal symmetries were almost always approximate. So as Nambu said, the moment you observe a symmetry, you should think about ways to break it. And this is sort of another concept in physics, which is called falsifiability. That is, if A implies B, then not B implies not A. So if a symmetry implies a conservation law, then violation of that conservation law means that the symmetry is not there. Okay, so this is also a philosophy of how to do science. And what the generalists try to do is to clarify the general properties of, for example, quantum field theory, and develop fundamental laws. So it was the progression from reductionism to generalism that led to spontaneous symmetry breaking, the work for which Professor Nambu got the Nobel Prize. So the thing is, he was basically a nuclear and particle physicist. But the nice thing about being at a university and at an institute like yours is that they are colloquia, and you go and listen to people in other fields also. And similarly at the University of Chicago, which was near the University of Illinois at Urbana, there was a new theory of superconductivity that had been developed by Bardin, Cooper, and Schreifer. Schreifer was a student of Bardin. Bardin, of course, has got the Nobel Prize twice in physics, and they had developed this new theory, and he talked about superconductivity as a phenomenon which was the microscopic phenomenon of which was called the Bardin-Cooper-Schreifer theory, and it was based on these Cooper pairs, which are the charge carriers of a superconductor. So it was different from electrons, etc. And also there was this interesting effect that in a superconductor, magnetic fields were eliminated. And therefore you have this superconducting levitation and things. So that was called the Meissner effect, and it was the repulsion of magnetic field by a superconductor. So in 1957, Schreifer gave a job talk at the University of Chicago, and Nambu, of course, being a professor then, was listening to Schreifer's job talk, and he came up, and he was very interested in that, and it triggered his imagination. So he said this, that my impression of the seminar was a mixture of admiration and doubt. I admired the fact that their assumed Hamiltonian led to a condensate, which is this Cooper pair, and formed an energy gap, which is, energy gap corresponds to elimination of the magnetic field. At the same time, the Cooper pair wave function implied a massive photon, so it violated gauge invariance. So there was this phase symmetry called gauge invariance, which was thought to be an exact symmetry for electromagnetism. And it was violated, and it requires the photon to be massless. But the expulsion of the magnetic field means that in the superconducting phase, somehow this gauge symmetry is broken. So how could that be? Because how could gauge invariance be there and a massive ground state exist at the same time? How could Meissner effect, that is the massive, it's like a massive photon, and gauge invariance exist at the same time? The doubt grew deeper and deeper in my mind as the BCS theory became more and more conspicuous, and it was, almost taken as gospel. And I think you're going to have another session in which you're going to hear about Phil Anderson's work, and Phil Anderson also was part of this group, of the superconducting group. So this was the specific phenomenon that Nambu was worried about in 1957. And what he wanted to do is not only find out what was happening at the quantum field theory level with the superconductor, but he wanted to see how those ideas can also be applied to particle physics. Okay, so there was this dual purpose in his mind. And then he told me it took 2 years to establish that the ground state need not have the symmetry of the Hamiltonian. So this was the big realization. This was what spontaneous symmetry breaking is all about. And you see it everywhere. So what happens is, for example, in a ferromagnet, when you describe the ferromagnet with a Hamiltonian or a Lagrangian, it has rotational symmetry. But you know that the ground state of the ferromagnet has all its spins aligned in one direction. So since it has all its spins in one direction, it does not obey rotational symmetry, because if I turn the ferromagnet, the spins will go in the opposite direction. So it's not a symmetric state. So, it's a ubiquitous phenomenon. And so then he had to work out how this symmetry breaking for the ground state gives the electromagnetic field a mass and forms a plasmon, and that is responsible for the Cooper pairs and the Meissner effect. It is a result of mixing of the two zero modes of the Coulomb field and this new field, which is called the Nambu-Goldstone boson, or Nambu-Goldstone mode, which he predicted. And I was able to finally come to terms with BCS theory. And see, this is his idea of generalizing a particular phenomenon and taking the mathematics of quantum field theory and coming up with a general principle that there are systems in which even though the dynamics may be invariant under a symmetry, the ground state of the particle does not carry the symmetry of the dynamics. So this was called spontaneous symmetry breaking. That is, when it relaxes to ground state, the system spontaneously breaks symmetry. It's not a explicit symmetry. That is, you don't distort the symmetry in space-time, but it actually happens spontaneously when a system settles to its ground state. So this therefore was not called symmetry breaking, just symmetry breaking, but spontaneous symmetry breaking. And then Nambu said, okay, so this is a general phenomenon. How do I apply it to particle physics? And remember that he was studying the Yukawa Meson at that time, 10 years ago. So he was still interested in, particle physics and strong interaction physics. And he was particularly interested in why the pion had such a light mass compared to all other bosons. So then he said, okay, let me look at other symmetries. So by looking at chiral symmetry, which is a left-right symmetry that particles have, he was able to explain the origin of the pion mass as being due to spontaneous symmetry breaking. And he says, I wanted to show the possibility of spontaneous symmetry breaking in the clearest possible way so that it be understood by all fields of physics. In fact, my theory was more popular with condensed matter physicists than particle physicists. Okay, so he because he had gotten his idea from thinking about condensed matter physics, they loved him. But because he was throwing a new idea to particle physicists, they didn't like it. People are always averse to change, it seems. So, what do we gain? What insight do we gain from this part of his life? The insight that I gained is that one should never compartmentalize yourself. All fields in physics are ruled by a minimal set of guiding principles. And, so therefore you should be open to ideas from all fields of physics. You should not say one is better than the other, etc. They're all on an equal footing and they all have cross-fertilization between them. Meanwhile, Gell-Mann had proposed the quark model in order to, he had said that, all baryons are made out of 3 quarks. And he was not clear about how 3 fermions in a state, could stay, because it was a violation of Pauli's exclusion principle. So he then created these quarks as a mathematical entity. But Nambu, remember, the second phase of his 3-stage philosophy was that you should always try to find out whether the substructure actually exists. So he was always tempted to think that no, it cannot just be a mathematical artifact, it must exist in nature. So, but the thing is, how do we explain why matter is so stable that these objects just don't fly out of you, that you cannot ionize the nucleus again, strong interactions, I mean, just like you can ionize an atom, but you can't ionize you cannot pull the particles of the nucleus out, otherwise matter would collapse. And why doesn't matter collapse? You have 3, what keeps Pauli's exclusion principle good in the proton and the neutron? So he introduced a new quantum number. And all these quarks in the nuclei had this new quantum number, which is called color. And it was, they came in red, green, and blue, and their total color was white. This is just an analogy. It's nothing to do with light. It's just a new quantum number. And he developed it with Hahn, who is his graduate student. In his word, when I ventured to 3 internal degrees of freedom of the quarks, there emerged a beautiful symmetry, which was exact and not broken. And it was SU3 symmetry. And it explains, why at low energies, the quarks are confined in matter, and you cannot see free quarks at low energies, and matter is stable. Although, he is not given that much credit for this, because in his model, the quarks had units of charge which were integral, and later on it was found that the quarks have a 1/3 charge, 1/3 of a integer charge. So so he is not recognized so much, but the initial idea of this quantum number came from Nambu in his Han-Nambu paper. Then in 1968, by looking again at symmetries of how the masses of different particles depend on the angular momentum and other characteristics of the particles, Veneziano came up with a model to explain the masses that come when you scatter one particle off the other. You see peaks in the spectrum, and those are called resonances. And he could find some sort of symmetry in the way the masses occurred. And when he looked at Veneziano's paper, he was very intrigued. And the way he told me is that he looked at the diagram like this, and then he looked at the diagram like this, and then he looked at the diagram like this, and he came up with an idea. And he said that, so he came up with an idea in which he said, with a student from Syracuse called Goto, he said that these the quarks inside nuclei, they are held together by a potential which is a one-dimensional harmonic potential. So it's like a string. It goes as the distance between them. Okay, so that rather than 1/r², which is it's proportional to r rather than 1/r², which is the Coulomb potential, and and so since it's proportional to r, as the distance grows, the potential becomes stronger. So the quarks cannot come out of the nucleus, right? Because the force becomes so strong that they are drawn back in. So unlike the electron, which can go away from the atom. So this was what, and with this simple idea, he wrote down a Lagrangian, an action, which is called the Nambu-Goto action. And it's interesting that, the whole idea of strings developed in this context, in looking at experimental data. Now, strings are used in a different way as things which would lead to the unification of gravity with other forces. And, not much experimental, no experimental evidence has yet come for them. So, we're going full circle. We used the strings to get this, we used experimental data to get the string potential, but in a different domain. And now it has gone to a different domain and struggling with finding some expression, experimental expression. But this paper would have been lost because he intended to present the work at Kiev. I thought it was interesting that Kiev should come up in the present political situation, in Kiev at a conference. But on the journey before the conference to the airport, his car broke down. And so he scribbled the formula called the Nambu-Goto action on a piece of paper and sent it by mail. The proceedings were never published, but the idea of string theory was born, and one can never find this paper. It's very difficult to find this paper because it was never published. But the whole idea of strings came from this note that he had mailed. And the thing is, he really thanks the organizers of the conference for making it known. And so people were so nice to each other at that time. Now they would be just fighting competition and, one person suppressing the other. But it was so nice that he got to, that the whole idea of strings would have just not been there if it hadn't been for, this type of support that the scientific community gave each other at that time. So, so what was the essence of Nambu's work was unity in diversity. So while working with Professor Nambu, I always saw that he looked at a problem not just from the particle physicist viewpoint, but from condensed matter, even from the philosophical viewpoint, or even from the quantum optics viewpoint. You know, he would look at the problem and he would use tools from different, and he would suggest to me, use these tools, use that tool. And this really served me well later in life because, you know, as you heard, I work on the intradisciplinary relations between cosmology, quantum optics, strings, um, uh, uh, particles, you know, neutrinos, etc. So it really helped me to look at these with different lenses. And he was always picturizing the situation. He, as I told you, when he looked at the Veneziana amplitude, he was trying to picture the situation. In that sense, he had some sort of a stereoscopic vision. Later in his life, this is very interesting, he turned to questions of biology. And then remember, this was 1980, later in life, it was around 2000, when he was, you know, around 80 years old, to breaking space-time symmetries. So he thought of what would it be like to break Lorentz symmetry. And one of his last lectures was that maybe we can look for it in neutrino systems. And at the moment, I'm working on neutrino systems, and they are planning to look at breaking of Lorentz symmetry in neutrino systems. And this, remember, this was 2000, and they're thinking of looking for it in the last 5 years. So again, you know, his idea then may become a reality or may not become a reality. The testing is taking place. And this is another absolutely Cassandra-like calculation. His last calculation was in biology, and it was to study the organization of virus-sized particle in a cusp-like container and show that they violate gravity and entropy. And I thought this was a very good way to show his prophetic nature, because we're suffering from these virus-sized particles. But in a way, it has allowed me to talk about his life with you. And I hope that some of the, the lessons that his life teaches us in some way affect your scientific worldview. So he was a seer who foretold the future. He remarked that the future of science is when theory and experiment join hands, when research becomes a collective enterprise. Remember, he's of the old school of thought where people support each other in science. People, you know, discuss science. They take views from each other. They give people credit. And although he got credit, you know, 60 years after he had done his seminal work. So here are the two Eastern scientists who were responsible for a lot of our knowledge about symmetry together, Professor Abdus Salam and Professor Y. Nambu. And basically, these two are the reason that I'm in physics, and they have really affected my life a lot. And so therefore, I really believe that there is nothing Western about science, that it is just it's a way of thinking, and that all civilizations have it as its legacy. And I'm tired of, Western. These two are not Western people. And this is on his 60th birthday, all of us. And you can see that I am sitting there in the red shirt, and Chumit Das is sitting next to Professor Nambu, and Spenta Wadia is in green. And so we were drinking to his health, and now, now we drank to his 100th birthday. And so what we did was that we brought out a centennial issue of Indian scientists, some of the Indian students who were affected by Professor Nambu's work, and it has been just published. And this is the editorial. And I will end by saying the last words that Professor Nambu uttered in public, and they were a quotation from Galileo, which is "Aperio si muove," which means "and yet it moves." This was what Professor Nambu ended his last talk with. That is, physics moves along. Physics has a bright future, as yet it moves. And this actually is also let me just stop share. Okay, this actually, I will just end with this. So this actually has been this, and yet it moves, was what Galileo said about the Earth moving around the sun, and yet it moves, and it's not stationary. And so there have been symphonies. But I would end with the symphony of "and yet it moves," and yet it moves, and you are the people who are going to take it forward. Thank you.
Thank you so much, Dr. Bambah. That was a wonderful talk. Um, uh, I'm sure that sharing your experiences and your journey with Professor Nambu was so eye-opening and motivating to all of us, especially the small things like how he used to keep himself, or how he used to wear black suits all the time, and how he brought two completely different things together. It motivates us to look everything from every lens, not just a certain perspective. It opens many doors and windows that were shut earlier. And it was just a wonderful experience to listen to you, and how he was into Indian philosophy, and how it's all brought together by this wonderful talk. So finally, we do have one request. Can we take a screenshot of this? Yeah, so if anybody would like to switch on their videos, feel free to do so. If you can do it right now, it would be great. I think in this online platform, this is what's missing. So if anybody could switch on the videos, that would be great. Oh, nice. Hi, everyone. Okay, I think let me just make this view a little bit better.
Naveen.
Right, so great. I'll just wait for a minute then, everyone.
Right. Sunil Kumar, hi.
Thank you so much, guys. I think I've taken the pictures. Thank you so much.
Okay.
All right. So finally, thank you, Dr. Bindu, Dr. Bambah, for having this wonderful session with us. And finally, we highly appreciate your presence and wish you all the luck in your future endeavors.
Well, I'm retired now, so the luck is for me to enjoy life now. I retired just last month, so.
I think I'll just like to add this. Like while you were speaking, ma'am, I could imagine, hearing these things some 10 years down the line in the textbooks of students, and then imagining who these people were who did all this work. And to hear that from you, like this live, was really nice. Like when we read through the books, Einstein did this or someone did this, we keep on imagining, what kind of a person that Einstein might
and
have
the
been.
ice cream truck.
Yeah,
going to the ice cream truck just to get a glimpse.
Yeah, in fact, he has a picture of Einstein with the ice cream truck, but I didn't. But it's I haven't been. Then it must. He showed it to me, but that was like 40 years, many years ago. So,
Also, finally, we place our gratitude to everyone who joined this session, and thank you for your active participation. Additionally, I would just like to highly appreciate the science club coordinators, the volunteers, Professor Sunil Mukhi, who played a major role in organizing this event, as well as Professor Rajesh Nath for flawlessly bringing this all together. Finally, thank you all for making this event possible. It was a remarkable event. Okay, so we've got a chat. Just a second.
Oh, do we have something? Really wonderful.
Yes.
Oh, thank you.
Thank you. All right. So do we have any questions? Please put your questions in the chat box or unmute yourself. I think if you would like any, if you have any questions, please feel free to unmute yourselves. Okay, so I think we've heard a question.
Can we conclude that? Let me just see, what is this?
Can we conclude that the nucleus and the quarks are wave functions?
Oh, well, all particles have wave functions. All particles have wave functions. Actually, you know, the quark, so you know that there is a de Broglie principle that all particles have a dual nature. Okay, so the smaller the particle and the slower it, so for example, the wavelength associated with quarks would be it would be h cross divided by its momentum. So once it is confined and cannot move, yes, its wavelength will be very large, will be larger than if it was able to move. The h cross by p. Yeah, all particles have a wave-like nature. So not just quarks, everything. It's just a question of how big the wavelength is. So if you're massless, your wavelength is very large. Is there any experiment? Can you read the question?
Is there any experiment which can prove the existence of strings?
Well, see, strings as holding together quarks in nuclei, there are experiments, but strings as the unification of all four forces, there were some things that were predicted for the Large Hadron Collider, but they were not seen. And so now one is looking for some sort of cosmological evidence for this. Of course, Professor Sunil Mukhi would be the person who tell you more about this. But at the moment, for the strings which are responsible in string theory for unification of forces, there is actually no experimental evidence yet, which is one of the reasons that it's a controversial field with many competing fields also with string theory. You know, it's a highly mathematical competitive field because at the moment, apart from the fact that, as I told you, that it's a Dirac mode of thinking, that the mathematics is logically correct, but there is the predictions that were thought would exist did not turn out at the LHC, but now the predictions are at a much higher energy. So we haven't attained energies or seen cosmological evidence for the existence of strings yet, but we hope that we will. Why are quarks associated with why are quarks associated in the nucleus in a compacted way? Why not spread about? Okay, no, the reason is the following. The potential which binds the quark together increases as the radius of the nucleus increases, okay? So supposing that you try to, it's like a rubber band. The potential between two quarks is like a rubber band. So if the quark tries to go out of the nucleus, the rubber band pulls it back. That was Nambu's main idea, okay? Which is why it's called quark confinement, which is why it cannot escape the nucleus. So, you know, the wavelength it has, as you said, is very, very small. It's made small because as soon as you try to take the quarks out, the force field, which is the rubber band, pulls it back. So think of it as a rubber band. Oh, and somebody says, what about his work on biology? Unfortunately, I don't have that. This he wrote in a letter to me. I don't have an access to that work, but if I do, so because, you know, you see how Professor Nambu works. He in his drawer, you'll find 100 calculations. When he was going to a conference, he put the calculation on a piece of paper and send it, you know. So I hope that somebody has, you know, found it and worked on it, but I don't have the calculation with me right now. Sorry about that. But I just thought it was interesting because he did write to me about these things, and it was 22 years ago, and you know, and now we have such a virus, you know, and it's doing funny things when it collects.
So do we have any other questions? Covered it all. Okay, I think we have one more question ahead.
Science, in a way, is seen predominantly dominated by Western people. How has stereotype changed over the years? Is there any discrimination? You know, there is discrimination, but a lot of people have broken this barrier. For mathematics, the barrier was broken very early because of Ramanujan. You know, once it is, you know, but the other thing is that sometimes when we just try to mimic the West, we also destroy our own originality. So, yeah, so there was a lot of prejudice earlier, but because we have had such good scientists, like beating the Westerners at their own game, like, you know, Professor Sunil Mukhi, Professor Ashok Sen, and Professor George Sudarshan, etc. I think that as far as Indians are concerned, you know, everybody has taken Asians, you know, everybody has taken for granted that Asians are. But with regards to both race and women, science is not either gender friendly, nor is it race friendly. And so now what is happening is that people are looking for diversity in science, you know, and yeah, and you know, one of my other teachers was Professor S. Chandrasekhar, who also was a Nobel Prize winner. And when he first went to America, first of all, his theory about white dwarfs was not taken seriously. And Eddington kept on telling him that it's no good. Then when he went to America, to the University of Chicago, he went to, at tea, there was a person called Bliss, who used to work on variational principles. And he was asked to shake hands with Professor Chandrasekhar. Professor Chandrasekhar was very dark. And so he says, no, I cannot shake hands with him. Then Professor Chandrasekhar replied that, you know, in India, I would not shake hands with you either. You are a Malaysian. Because so he, you know, he was very insulted. But then, you know, Professor Chandrasekhar became one of the best physicists that Chicago ever produced. So, I mean, so, you know, there was, but I think now, at least with regards to the Asian countries, it's more jealousy now than, you know, than discrimination, you know. But, you know, even Professor Sudarshan, he proposed the same theory as Feynman and Gell-Mann for weak interactions, and he never got the Nobel Prize. He proposed the same states as you know, Glauber, coherent states, and Glauber got, and he never got the Nobel Prize. So he was looked over many times. So I don't know. If Nambu stuck in any problem, or when he went to the US, he was like, these people are smarter than me. What did he do in such situations? Well, he worked harder. He tried to think, you know, he did have a lot of feelings of inadequacy, almost to the point of nervous breakdown, he said, when he first went to the US. But then I think as he realized that his ideas are being accepted by other people, and that he has these fresh ideas, and that I think the other people at the institute appreciated him, and it's through appreciation that he got the confidence, which is why I think that it's very important to learn this about science, is that appreciate the other person, not become jealous of them, you know, appreciate another person. What was the influence of Dr. Okay, so I told you that So I did work on the string model of hadrons for a long time after the original string, not the later string. And I tried to see, you know, how the properties of new states like quarkoniums could be explained by, and we got very, very good results. We have a potential that we proposed. And then after that, Nambu told me to look at experiments and theory together. So, and also to look at other perspectives. So I work on looking at, you know, regularity again in the production of particles in experiments. And if I can explain it by using, for example, the theory of in quantum optics or condensed matter physics to explain these things. I've also worked on baryon asymmetry problem. I worked basically, the way his thinking has influenced me is to free my mind from the shackles of being in one discipline only. To look at things with different lenses. What are some areas? Oh, okay, which may be explained by string theory. Well, sorry, and click to exit. Oh, sorry. I don't know what happened. Yeah. Right. Quantum field theory has given us the only reason why we consider theories other than quantum field theory is because there is no quantum theory of gravity. Okay. And within quantum field theory, it is very difficult to have a theory of gravity because space-time itself is the dynamic thing in gravity, you know, curved space, etc. So we don't have a quantum theory of gravity, which is why we have to look for other theories besides conventional quantum field theory. Okay, I think that's all.
Yeah, that's all.
That was nice. So many nice questions. It was very nice. Great.
Oh, I think we have one more question.
Do you think the more cooperative aspect of scientific community has reduced over the years due to, as you wrote about strings on a paper and was supported by the community? I think so very much, yeah. The only place where cooperative aspect has increased is in experimental physics, because experimental physicists tend to work in large groups. And that's why the World Wide Web was invented. So in that way, I think the internet is maybe the solution, and Zoom meetings for cooperation. But yeah, I think people are just trying to increase the number of papers and fighting with referees and all these things, and morale is very low because the competitive nature is very high. Thank you, Vaishnavi.
Do we have any more questions? That's all. Covered everything.
Okay then.
Right. Okay, thank you so much for this wonderful session. Thank you all for being here.
Very much for having me. Thanks.
Thank you so much. We'll end the session now. Thank you. Thank you, everyone.